ये जूम का आ रहा है। हेलो हेलो, सुनाई दे रहा है नित्या? तो ऐसे लैग होके आएगा। यहाँ पे वीडियो की कुछ भी नहीं करना पड़ेगा। हेलो, सुनाई दे रहा है क्या?
स्ट्रीमिंग का ऑप्शन आ रहा है इसमें।
गोपाल, लिंक तो नहीं चल रहा है बोले? कौन सा लिंक? फिर से जाओ यूट्यूब पे।
Studio.youtube it's not working.
वो उनके लिए है। बात कर लिया।
तो एक काम करो, तुमने नहीं एक कोई बात नहीं, तुमने कौन सा खोला है? ये लिंक लो, ये वाला लिंक
नहीं डालना है।
ये वाला लिंक
गोपाल ने डालो।
ये इस वाला लिंक दो। इसका लिंक कहाँ से कॉपी होगा? हाँ, ये लिंक कॉपी करके भेज दो।
वो लिंक ग्रुप में डाल दो ना। ये वाला डालो। नहीं डालना। ऑडियो वाला कनेक्ट। अरे ठीक है, ऑडियो वाला कनेक्ट कर दो। ऑडियो वाला कनेक्ट कर।
हेलो, ये वाला लिंक देख लो। See if you can hear me, huh? Hello. Hello. My sound is coming or their sound? It's fine.
वो भी आ रही है पर दोनों आ रहा
हाँ, this link is working. Yes, yes. No, this is not working. ये काम कर रहे हैं ना? Okay, good. So this is working fine. ये बंद कर दूं? It is working fine. It's working fine.
देख लिया, चेक कर लिया। अभी स्टार्ट करना लेक्चर।
वो जो आपने सबमिट भेजा
कैसे करेंगे? नहीं, उनसे जूम से कनेक्ट कर दे रहे हैं, वो शेयर कर देंगे। जूम की लिंक भेजिए। जूम लिंक शेयर करना है ना। देखो, जूम की लिंक शेयर करो। जूम की लिंक नहीं वही क्या खुला होगा? ये जो भी है, मैं देख रहा था यार, कैमरा ऑफ है। ये बंद कर दो ऑडियो। क्या ऑडियो?
So I will turn off this microphone.
लगाने पड़ेंगे, वो चालू कर। वो माइक, वो ये किसी काम करने में आता है।
एक और माइक है ना, वो भी देना।
Just to get, हाँ, should be okay.
तो दो माइक है।
हाँ, एक ही लेना है because we have to see which one goes into the screen. Should I share the screen?
Yes.
Yes.
ये तो रेडी हो गया। टेक्निकल ये देख लेते हैं।
बहुत छोटा दिख रहा है।
नहीं, वो छोटा ही है।
सर एक्चुअली दो माइक यूज करना है, एक लाइव स्ट्रीम पे ये हो जाएगा।
ऑडियंस के लिए। इंटरफेयर तो नहीं करेगा ना?
नहीं इंटरफेयर नहीं, इसकी जरूरत पड़ेगी।
नाम बोल रहा हूँ, लग रहा है ठीक है। फिर लगा उनका आवाज तो है, मुझे लग रहा है
आवाज से तेज है।
जरूरत पड़ेगी लगा। हाँ ये जरूरत पड़ेगी लगा सर,
ये तो लगाना ही पड़ेगा। कब से स्टार्ट करना? लाइव स्ट्रीम से स्टार्ट करें।
सॉरी
4 बजे इसको बंद कर देते हैं और
हाँ बैटरी बंद करता हूँ। नहीं काम कर रहा है, काम सब कर काम कर रहा है
दोनों ये भी ना।
हाँ
ये इम्पोर्टेंट अरे
कुछ कर रहा है जगहों पर। इसको मैं अभी बंद कर देता हूँ, एक बार हम लोग बंद करके हैं, एक बार फिर से करके देखते हैं कौन वो कर रहा है लाइव। आवाज आ रही है इसमें? हाँ हाँ ठीक है म्यूट कर दिया था। हेलो हेलो म्यूट कर दिया था मैं। ना ना म्यूट करने दिक्कत क्यों नहीं। हेलो आवाज आ रही है अभी? अभी तक नहीं आई। हेलो। हाँ ठीक है म्यूट कर दिया था। हेलो हेलो। ठीक तो है, ठीक है ठीक है। अरे बहुत लैग है यार, बहुत लैग है।
उससे तो कुछ कर नहीं सकते वो
हाँ
इंटरनेट की
वो
वजह
तो
से।
हमको कुछ नहीं कर सकते। नहीं नहीं नहीं, इससे आ तो रहा है। बस जैसे हमको यही करना है, इसको चार्जिंग को भी लगा। ए जब 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 स्ट्रीमिंग चालू होने वाली हो ना, जब चालू होने वाली है, ये क्या बोलते हैं स्ट्रीमिंग कब से होगा? 5 मिनट चालू, सॉरी मीटिंग। 5 मिनट पहले ऑडियो पहले से लगा, ऑडियो कनेक्ट कर। यहीं पे हूँ, जान नहीं रहा हूँ। याद दिलाना मुझे। एक इधर है, जूम से भी कोई ज्वाइन करने नहीं आता। जूम के लिए काम कर सकते हैं। तो एडवर्टाइज कर दिया गया था। वो
सर इसमें आप मेल एक बार चेक से भेज दिया।
कुछ अभी जूम पे डिपार्टमेंट वाले में डाल दें, डिपार्टमेंट में डाल दें, डिपार्टमेंट में डाल दें, रिकॉर्डिंग हो जाएगी। कैमरा सब चेक हो जाएगी। रिकॉर्डिंग रिकॉर्डिंग सही
इसमें हमने ये सिस्टम कभी यूज किया नहीं है, सीधे उनका सिस्टम यूज करते हैं। एलसी का ऑलरेडी बनी हुई है।
कौन चाहते आपसे इस मीटिंग को रिकॉर्ड करना है जूम पे? क्या मीटिंग करो
पे रिकॉर्डिंग होती है।
हाँ हाँ, रिकॉर्डिंग होती है Zoom पे।
अरे जस्ट ऑन रिकॉर्डिंग अभी नहीं टाइम कर रहा हूँ बस सर।
अब मत करना है।
ये तो लाइव भी जा रहा है तो वहां कैसे रिकॉर्ड होगा यूट्यूब पे?
कि वीडियो भी ऑन कर लें क्या? 1 मिनट क्या करना होगा?
वो लोग कनेक्ट हो गए?
हाँ हेलो डॉक्टर बेहरा, कैन यू हियर मी?
Yes, yes, I can hear you. Yes.
हेलो, गुड इवनिंग.
हाँ.
गुड इवनिंग डॉक्टर बेहरा.
Yeah, good evening.
आई एम नॉट एबल टू हियर यू. एक इधर माइक में कुछ इशू है क्या?
No.
बट वी आर नॉट एबल. कैन यू माइक में?
Yeah, now is it audible?
Yeah, now, yeah, now we can hear you. Yeah. So we will start at 4 o'clock sharp. Is it fine?
Yeah, it's okay.
There is a slight change. Like the earlier YouTube link was not working. Therefore, like few minutes back, I emailed you the new YouTube link.
Yeah.
Yeah, and yeah, this is.
Yeah, it's
So we will start in a few minutes.
Okay.
please share. Share. It's not a single connection. It's all virtual. But our English international is doing the same thing.
थोड़ा सा साउंड और बढ़ लगता है क्या वहाँ पे? इट्स वेरी कैसे सब लोग नहीं सुन पाएंगे.
वो तो है. वो जो
बोलेंगे सर वो सुन लेंगे, जो यहाँ पर बोलेंगे
इससे लगा वो
नहीं. जैसे जो सर यहाँ पे बोलेंगे ना, जूम के थ्रू जो बोलेंगे उनके लिए सर हमारे पास वो वहाँ उसमें हो रहा है, लेकिन वो सर बहुत तेज.
इससे करेंगे.
कनेक्ट कर सकते हैं.
इसको वो देने वाला वो
स्पीकर वाला कौन सा सिस्टम?
इस पे क्लिक करो. इस पर नहीं, इस पे क्लिक. स्पीकर्स में जाओ ना.
ये है
हाँ,
यही वाला स्पीकर सिस्टम को.
सिस्टम भी ये वाले ऊपर लगे हुए हैं हमारे.
ऊपर वाला स्पीकर
इस पे करो.
ये तो ऊपर वाला है. दिस इज वेरी लो. ये वाला है ना
ऊपर वाला करो.
Okay. Hello, Professor Behra, can you speak?
Yeah, is it audible?
Yeah, now, but it is now this computer, I guess. Yeah, you are audible. We are just testing our different speakers.
Okay, okay.
Anything? और उसमें कैसे जा सकता है स्पीकर?
इन पे जाएगा ना सर.
कैसे नहीं जा रहा ना?
जा सकता है. यहाँ पर माइक रख दो. कोई ऑप्शन नहीं है
सर स्क्रीन शेयर करने में.
सर. अगर वहां से कोई लोग अगर क्वेश्चन पुटअप करते हैं
हाँ तो कैसे?
हम सर मैन्युअली करेंगे उसको. यहाँ वो रख के माइक उनका फिर आवाज है.
तो अभी के लिए माइक रख देते हैं.
अभी के लिए माइक रख के कर सकते.
माइक ऑन. वही वहाँ पे ऑडियंस वाला तो इधर रखा है.
कनेक्ट कर लीजिए इसको.
एक और था ना, वो एक और लेपन माइक था ना. एक लेपन माइक तरीके का 2 था ना. उस तरीके का था ना 2. कल 2 तरीके के 2 माइक. ऐसा तो एक और था ना.
फोन कहाँ से हुआ है?
हेलो हेलो हेलो.
यहाँ पे रख के कर सकता है.
ठीक. नीचे होगा तो फिर नीचे होगा. यहाँ पर
फुल से कर दीजिए.
बाहर से बुला लेते हैं. वॉल्यूम फुल है क्या इसका? इसका वॉल्यूम फुल कैसे कर सकते हैं? वॉल्यूम अप कर दें इसका. फुल
इनसे सर इंटरेक्ट करना होगा तभी ये यूज करें, अदरवाइज मैं बता सकता हूँ.
हमने तो वो लगाना पड़ेगा सर ऊपर. उसको कर
एक्टिवली होना कोई भी सर ऑन करेगा तो वापस.
उनके कंप्यूटर स्लाइड में उन्हीं कंप्यूटर उनके कंप्यूटर में डालना पड़ेगा. ये कहाँ से है? चल नहीं रहा. मैकबुक की स्लो है. यूज करेंगे. अरे छोड़ो, मैनुअली यूज करेंगे. चलो
हैं?
चलो
नहीं वो उनसे बात है।
देखो क्या करेंगे जैसे यूज करेंगे और लेजर यूज करने कितना यूज करके कीपैड यूज करेंगे हाँ कीपैड यूज करेंगे एक मैं स्टार्ट कर दे रहा हूँ मैं स्टार्ट कर दे रहा हूँ उसको
यूट्यूब वाला लिंक स्टार्ट करो, यूट्यूब वाला लिंक स्टार्ट करो, मतलब दिखाओ मेरे को, मैं चेक करूँ क्या आ रहा है। तो मेरे को हेलो 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 हेलो, मेरी आवाज क्लियर आ रही है? एक बार ध्यान से देना। मैं जब बोल रहा हूँ नहीं आ रही को। हेलो 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 से यार ये वाला उनको दे दो। ये सर
Professor Behra, can you hear me?
Yes, I can hear you.
Yeah, so should we start?
Yeah.
Professor Behra, would you like to share your screen?
हेलो
Already on screen is there, so I will not be able to share. So you have to.
no so probably it would be awesome. Yes. Yes. Close करते हैं. No need, we have to share.
Dipankar is unshared. वो अनशेयर करेंगे ना वहाँ शेयर हुआ है ना
Unshare कर. Just wait a minute, we are doing it. Yeah, no, it's unshared now. Please try to share your screen.
Is it visible?
Yeah, it's a visible. Yeah, please make it full. Bring it to full screen.
Okay. Just a minute. Yeah, is it okay? Is it okay?
Yeah, no, it is on full screen.
Okay. So should we start?
Yeah. Audio or yeah.
Yeah, on behalf of Indian Physics Association, I welcome all the participants. Today we have a DAE Raman Lecture by one of the distinguished observational astrophysicists of the country. So the Indian Physics Association actually started founded in 1970, and the web page of these things you can find it out at TIFR, which is IPA 1970. And there are various chapters in Indian Physics Association. Indian Physics Association is roughly 47 chapters, roughly 4,400 members, and it is spread throughout the country. You can see that in the map, all the chapters here. And Roorkee is one of the oldest chapters of the IPA. It is roughly around 1970 itself. It was started at Roorkee when Professor S.K. Joshi was serving there, and actually he was the founding member of the Indian Physics Association. And the main motive of the IPA was to conduct the special lectures lacing with the national body, biennial awards, and it has also international linkage and memorandum of understanding with America's Physics Association, Institute of Physics in UK, and other huge with Asian agencies and Italian agencies. And this membership forms is actually available in the IPA website. If anybody wants to join, they can join it online now. There are various publications of the Indian Physics Association. The main one is the Physics News, IPA Bulletin, which is published quarterly, and online also nowadays it is available in TIFR sites. And these are some of the glimpses of the recent IPA magazines which have been published. IPA also does publish some of the monographs and some books also time to time. But for the last 2-3 years, no new things have been published, and in near future, some of the new books will be published from the IPA. IPA also instituted many awards through by endowment grants by the various people. One is R.D. Birla Award in Physics, Murli Chugani Memorial Award for Excellence in Applied Physics, Iyengar Memorial Award in Experimental Physics, Bhuti Foundation Award in Theoretical Physics, N.S. Satyamurthy Memorial Award, S.N. Seshadri Memorial Award, Ashwini Kumar Rath Memorial Award, which is dedicated to nuclear physics, Rahul Besu Memorial Award for High Energy Physics, and Professor C.V.K. Baba Award for the Best Thesis Presentation in Nuclear Physics, Anil Kumar Bharti Bhatnagar Award for Best PhD Thesis Award in Solid State Physics, C.L. Bhatt Memorial Award, and Indian Physics Association Physics Olympiad. And these awards are distributed in many age group. There are like R.D. Birla Award and Chugani Award, P.K. Iyengar Award belongs to a very, very senior physicist, and other awards to the mid-career physicist, and few of the awards for a very young physicist. So these are every year, it is advertised in IPA website and all to the IPA members. So you can nominate to the deserving candidate. And these are the presently, these are the office bearer of the and LC members of the Indian Physics Association. President is Professor S.M. Yusuf from BRC, and Vice President is Professor Subhabati Goswami from Physical Research Laboratory. General Secretary is Dr. Aradhana Srivastava from BRC. Treasurer is from Dr. Prabhu from the TIFR, and Joint Secretary is Professor Samit Mandal from Delhi University. IPA since 2017 has a strong gender working group, and these are some of the members of the gender physics group. And the main motive of the gender working physics group is to highlight the achievements of the women physicists by means of like awards and sensitizing the women physicists throughout the country. This is the TIFR website from Indian Physics Association. And to join IPA, you have to go to its homepage and click for the new registration. You will get that thing, and everything is online. You can attach your photographs and also transfer. And once it is approved, your form, you can transfer the money, and you will be informed for your membership. So I request all the participants in this meeting to join IPA. There are various forms of membership. One is life memberships, another is patron membership, and the student memberships. So I request all of you to join. And the present lecture, the DAE C.V. Raman Lecture, it is sponsored by the Department of Atomic Energy through the BRNS. And in this lecture, we select 5 eminent scientists per year in different places of the India to give a lecture. And very recently, we have persons like Professor Srikant Sastry, Professor Poonam Chandra, Professor Sandeep Patil, and others who have given this talk. And today's talk will be given by one of the distinguished observational astrophysicists of the country. So now I request Dr. Akhilesh to to start the program and introduce the speaker.
Thank you, Professor Behra.
Yeah.
Now I request today's speaker. Mic. यहाँ से नहीं वो इस रिकॉर्ड कर रहा है.
Good afternoon to everyone. I am delighted to welcome and introduce Professor Dipankar Banerjee, today's speaker. Professor Banerjee did his bachelor's degree from St. Xavier College and master's degree in theoretical physics from University of Kolkata. He has obtained his PhD from Indian Institute of Astrophysics and completed 2 postdoctoral tenures from reputed institutions in Europe. He returned to the Indian Institute of Astrophysics, Bangalore, and was promoted to professor in 2016. At present, Professor Banerjee is the director of the Aryabhatta Research Institute of Observational Sciences, ARIES, Nainital. Professor Banerjee's area of interest is the sun and the solar atmosphere. His work involves theoretical and numerical modeling using data from ground and space-based instruments. His work has enriched our understanding of the sun and its impact on space weather. He is the co-chair of the Science Working Group of the ADITYA Mission. ADITYA is the first dedicated Indian mission to study the sun. He is also the project coordinator for the National Large Solar Telescope Project, NLST. NLST is a proposed 2-meter ground-based telescope planned to be installed at a Himalayan site. He is also involved with NASA's Punch mission. Professor Banerjee has more than 120 reviewed publications with around 4,000 citations in international journals. He is currently supervising 6 PhD students, while 11 of his students have completed their PhD. So with this brief introduction, now I invite Professor Banerjee to give his talk. Thank you.
ये सभी आवाज अच्छा 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 ओके ये हाँ मेरा तो आवाज तेज है अच्छा लग लेते उसमें नहीं होगा वो अच्छा अच्छा देख लिया कर रहा था वही it was देख रहा था नहीं वो करना पड़ता है हाँ ये बिकॉज दिस इज एक सेकंड वो ऑलरेडी minute for it doesn't matter कोई बात नहीं हाँ मैं कीपैड से कर लूँगा Thank you very much for inviting me here for this lecture. I think first thing is I should become a member of IPA, and you have given me the references. Incidentally, I see many of my colleagues actually member of the Executive Council. Even the Vice Chairman was just 1 year junior to me in Kolkata University, and we did theatre also together in our alumni So it's nice to be here. I think IIT Roorkee has become a second home for ARIES. So Aryabhatta Research Institute, Nainital, we are a small institute, but we do host, one of the country's largest telescope, and it's a beautiful place. So I have some leaflets. There are two things which I will be talking about. So I'd like the students to, just please distribute them so that they can carry home some, small little information about our institute as well. So again, thank you very much for inviting me, and I hope this will be a sort of, many such lectures in future, because we do have a MOU between IIT Roorkee and ARIES. We have a joint PhD program, and we started with a lot of joint programs to be initiated. Of course, the students are the best to carry out these programs. We will only make the forums, and I am happy that I think few students have participated in our summer school program and other workshop. But I think I see another old colleague of mine. He was a young student when I was at IA. So I think the point is that now we are into a domain of multidisciplinary research as well. Astronomy, astrophysics do need expertise from multiple branches of not only physics but engineering as well. Another subject, there are biologists which is coming into astronomy because there is a new subject called astrobiology. Of course, nuclear physics and other things has been there for ages in terms of astronomy. So I think this combination of a small research institute with working together with the IIT kind of much larger forum is really in need of the hour. So I hope my lecture will motivate you a little bit on the subject which I work on, but there are plenty of other things which we can work together. So please feel free after my talk. I mean, during my talk or after my talk also you can ask questions. But I'm here till late in the evening. If students wants to just have a separate interaction, I will be more than happy to do that. I love spending more time with students than I'm bogged down by administration too much these days. I want to come out of it and interact with you. So you see pictures of our observatory. That's the one campus here. That's my office here. But these are the telescopes which I will be talking about very briefly before I go to the subject, because I work on our nearest star, the sun. So I will talk about primarily a brief introduction about solar physics, very brief, and then we'll talk about this mission, our own ADITYA L1 mission, but not to go into very big depth. So if people are interested, please do come and interact with me. So this is our campus where we live, and this is the Haldwani in the plains. This is our new campus in DAE near Mukteshwar, which hosts currently, this is the largest telescope from this part of the globe, called the 3.6 meter DAE optical telescope. We already had a 1.3 meter telescope, which is a little more than 10 years old. This I call sometimes our PhD students' toy, because this is only for our PhD students. Nobody, in fact, the PI of the proposer has to be the PhD student of ARIES. So if you want to collaborate, you have to collaborate with the PhD student to get the time in this. That includes me. Of course, this is a national facility with the open call. Anybody within the country can apply for observing time, and it's typically 3.5:1 now. Like 3.5 times oversubscribed. This is a very new facility, 4 meter liquid mirror telescope, which will be formally inaugurated actually on 21st of March. We'll probably hear about it more in the media all over. This is a very interesting thing. If I find time, I will talk about it a little more. This is the close-up of the 1.3 meter telescope, and you see the beautiful Himalayas in the background. So it's not a bad place to work. After the whole night of observation, you can take a cup of tea and enjoy the morning sun over the Himalayas. This is the liquid mirror telescope which I was referring to. You see, for a telescope, normally in the earlier old days, you either have a lens or a mirror. But larger the telescope, mirror becomes, I mean, the lens becomes much more challenging. You have lots of errors for a thick lens, you all know. So the solution was always a curved mirror surface. But larger the mirror, much more complication in terms of the stability, in terms of its surface smoothness, and so on. So suppose you pour mercury, which is a liquid, and then pour in a curved ball, say in a shape of a parabola, and then start rotating that ball. So if you pour mercury, it will actually spill to the edges, and it will take the shape of the ball. So at a comparatively lesser cost, you are able to get a very good reflecting surface. Other also issues with the mirror and all that, keeping the mirror surface clean and it's polish and so on so forth. So periodically 2-3 years you have to polish it and so on. Here mercury gets a little contaminated, and then you can clean the mercury much more easily. Of course, there are lots of protocol to be followed in maintaining a mercury. I just bet your director that he's aware of all this because he comes from chemical engineering background. It's hazardous, so there has to be a lot of protocol to be followed to use mercury. People wear masks and PPEs and all that to even go inside that telescope building. So so this is a new facility, but it is always looking at the sky. So this is going to be formally inaugurated. We had our first slide 2 months back. Essentially, it means that within this zenith, say 8 degree, 4x4 degree, whatever object comes, it is capturing. It can be a small satellite, it can be a distant gamma ray burst, it can be a space debris, it can be a good star or a supernova explosion. So that means millions of objects are there in this in this frame. So this is a perfect data for AI/ML application, because you need a fantastic data pipeline to identify what object you are targeting. So that you need to know the characteristic properties of the object, where this object is expected. So suppose you have 1 million objects in this, and you know already from your catalog that these are the objects which is supposed to be there. But suppose you find one object which is not there in your catalog. So that's the discovery, right? But now you have discovered one object, or a big supernova explosion, or a gamma ray burst in somewhere, or a two black holes merging, giving rise to a gravitational wave, but it has an optical counterpart. You detect that, but then you have in the next door a 3.6 meter very large telescope with all sophisticated back-end instrument like a spectrograph, with infrared, high resolution, and so on. So you can then characterize the properties of these objects. It's just not enough to these days, in a modern day, just to identify any object. You have to say what this object is and why it has become so bright, or whatever properties you observe just by imaging. So imaging do not really give you the complete understanding of the object. So that way, a combination of imaging and spectroscopy is the modern days, astronomy era. And we have this facility now in this same campus. So that's the 3.6 meter telescope. I should have a man sitting here. So it's a mammoth structure. You can imagine it's sitting on the top of this mountain and looking at the sky. Our students are really becoming master in astrophotography as well. So this is a good example of, these are the star trails. So our students do enjoy their life, I think, while doing the research as well. So that's a very brief introduction about where I'm coming from. Now I will go into my subject, the very old sun, our nearest star. The sun is a very normal star. It's middle-aged. You don't have to worry about too much of the jargons, but basically the stars are formed from interstellar medium. It goes under a stellar evolution, and after spending a lot of time in its middle age, it becomes a big star, red giant, and then can die as a supernova and so on. So for your information, we don't have to worry about next billion years or so about the star killing us and so on. Before that, we will kill each other. So not to worry about that part of solar physics. But it is a special star because it is the only star which we can really see the details, because most of the objects in the sky, we study them as a point object. We really cannot resolve them. We can't see their surface, what is happening, and so on and so forth. So that way, whatever we learn from the sun can be really basically extrapolated to other, astrophysical scenarios as well. Of course, it is a spatial star because it provides almost all our energy. Our existence is because of presence of sun and an appropriate distance away. And since this is a, physics, probably major physics students, I can just spend 3-4 hours to see how it is a unique laboratory. You start from nuclear physics right into the core to, plasma physics. We have a plasma physicist here. You talk about spectroscopy, atomic spectroscopy, molecular spectroscopy, particle physics. The fundamental problem of neutrinos was solved from solar experiment. So really, it's a wide, applications. And as you probably from a brief introduction you heard, I had no clue about astronomy until I went to Bangalore for my PhD interview. I actually gave interview in physics and astrophysics. I was not selected in physics. I was selected in astrophysics. So that's a real fact. But it actually, changed because astrophysics is not a separate branch. It is just, few applications are different. So that is also some message I normally try to convey to the students. You don't need to really know about astronomy. I still do not know. If you ask me which constellation will be seen and all that, I said, oh, app mein dekh lijiye. मुझे तो मालूम नहीं है कितने बजे मून आता है जाता है ये भी मुझे मालूम नहीं है. So the point is, of course, that a lot of people are passionate about astronomical objects from the childhood, fascination and all that. It's very good. But even without that, you can study astrophysics just as a laboratory of different branches of physics. So that's how I came from. And then this particular guy, sun, like all stars, are very dynamic. Although we all the time we see that that guy is there, we don't bother. It's there. It's emitting fixed amount of energy, and we think it is constant, which is also strictly not true. And if it doesn't emit the same amount tomorrow, then it's really going to have big impact on our, our climate, our existence, and so on. So that's a kind of variability one can study, which is a long term. Then there are variability of this image is taken from a NASA satellite called Solar Dynamic Observatory, and I'm looking at a coronal region here, and these regions you see is comparatively brighter as compared to the other region. So now we know that all this brightness or plasma which is confined in this particular region is because of the presence of a strong magnetic field. You will see these are called sunspots. These are concentrated magnetic field regions. And because of the presence of these sunspots of opposite polarities, a huge amount of material is confined within this area. And that's why they are brighter. So these are called active regions. And in the neighboring regions were historically called quiet region. And I will show nothing is quiet in the sun. Every part of the sun actually has some dynamism. It's just the energies are different. The spatial scales are different. The time scales are different. So this is again a time scale which we have to worry about. And this huge explosion which you saw here, they will travel. I will show you many more examples and how it can affect our interplanetary medium and our near Earth environment. That is what we have to worry about. And it's a laboratory for different branches, which I already mentioned. So these active regions are now known to be strong magnetic regions. Who first looked at or sort of identified these guys? None other than Galileo Galilei. It was just newly invented. And he looked at the sun from his not just Newtonian telescope, which was discovered a few years prior to that. And then these are his drawing. These are his drawing. It's been animated. Just subsequent drawings have been just added together. So what he noted was this kind of small little dark regions. Of course, he did not know at that point of these are magnetic regions because magnetic field was not known. But then what he noticed that this guy is changing its position in subsequent days. So that is only possible if that fellow is moving or rotating about his own axis. Of course, he did not know sun is not rotating as a solid body, but it's moving differentially at that point of time. But he already noticed that these guys, they come at certain latitude. Actually, north is here, south is there. So it's actually tilted because of the ground observation. In the space observation, we always correct it. North-south is always aligned with the geographic north-south. But here he noticed that this guy is moving subsequent day, and from that he inferred that sun is also rotating about its own axis. So these were all, important information later on. We every day look at the sun. Some days there are nothing. They look boring. Those guys are not there. Some days they are there. So that's also one need to explain why the sunspots are there in some days, and they're also there in certain locations, not in every location. Are there prescribed locations where they will come? So we all are now understand all that. So they always come in pairs. You see this, and this is a typical size comparison with the Earth. So you can imagine that how much energy is contained in these regions, and if these regions energy is dumped into the interplanetary space and coming towards us, we are in trouble. Thankfully, we have our magnetic field which protects us, but now we are going often outside our magnetosphere. So the assets which are there outside the magnetosphere is all endangered by these, a huge amount of energy. So how sunspots are formed? So now we understand that sunspots are magnetic structure that emerge from the beneath the surface. They are like these flux tubes. We call it flux tubes, like rubber tube. Millions of magnetic field lines. If you compose together, then you can think about in these kind of structures. And these structures, when they emerge out, you get the bipolar region. But sometimes, because of certain entangling and instabilities, these structures will also, give rise to a huge explosion. And whatever material was confined with that, you saw they were traveling into the interplanetary space. So this is the big solar storms which we refer to when it happens through a process called magnetic reconnection. Means in opposite magnetic fields, they're forced to come to each other, and then the magnetic energy gets converted into heat and kinetic energy and so on. So that's a short time scale variability. As I mentioned, that my title today is to understand the variability of the sun of different time scale, spatial scales. The shorter time scales have our near Earth everyday impact, which we call it space weather. And this time of variability, which I am depicting here for 400 years, what is shown here is yearly sunspot number for last 400 years. So immediately you see that there seems to be a cyclic behavior, that the sunspot number are sometimes very large, sometimes they are very small. So when there is lots of sunspot, we call it maxima. When there are very few sunspots, we call it minima. But you see the amplitudes do not seem to be always the same. So obviously it's not a very simple sinusoidal equation which will represent it. It's a nonlinear process. So now we understand it is a dynamo which is probably acting inside the sun, which is responsible for this. But then dynamo has a lot of parameters which is responsible. As you know, when you ride a bicycle, you ride the cycle, you basically convert your kinetic energy into power as a light. So here the sun is rotating differentially. The equator rotates actually faster than the poles. And also inside the sun, I did not mention so far, it's convective. It's a convection. 30% inside the sun is convective. So a combination of the convection and the rotation, runs the dynamo. But then again, we see lots of fluctuations in these, like these amplitudes are different. It's not that always the periods are also very fixed. Typically, it is about 11 years. That's why they called it 11-year solar cycle. But, we need to really find out, why this, cycle is so much, varying at different time. Of course, now we understand it is a completely non-linear process. It's not very easy to predict it even. Also, what is to be noted here is all the way back around 1650 to 1700, there were hardly any sunspots recorded. Of course, telescope was already discovered, so it's not that people could not see sunspot. So what is the mystery? We still do not understand completely. It appears that there was probably sunspots, but they were probably far too small to be able to be detected by a 4-inch kind of typical telescope. But why they were small, that also we completely do not understand. So these are called grand minima. So now people do simulations going back to the history, and they find, there are people in India also who have predicted there probably have been 20, 30 grand minimas in the last millennia. But now the question is, what is the effect of this? During this period, the Europe was, extremely cold. The Volga River was frozen for 40 years. So that really we cannot afford in today's modern day. So this was discovered by Maunder. It's called Maunder minima. So this has enormous impact on our climate. And as I mentioned, it is important to find out that whether such grand minima can occur or not. So this is again a different kind of long-term variability which we have to worry about. And you can imagine the physics of understanding the long-term variability is quite different as compared to understanding the short-time variability of flares and solar storms and so on. So that's what makes life interesting in the case of the sun. And fortunately, because of whatever different path I have taken, I had to really look at both these problems. To some extent, sometimes in your career, you are given some responsibilities. I was given a responsibility of digitizing Kodaikanal observatory data, which has been looking at data for 100 years plus. So I said, I have no clue about long-term study of the sun. I only will look for a few minutes and seconds variability. I have not looked at 100 years variability. Director said, nothing doing, you have to do this digitization program. So then it becomes boring. Unless you have a science interest, why will you take a research, this kind of admin responsibility? So I motivated myself. Obviously, this is only possible when you have good students. So I could grab some good students, and I got into that business, and I really, really enjoy. And then this particular data after digitization is really, really globally used, and we are all very proud of that. So this is the solar cycle of the real past. As I said, this was the period we still do not understand. These are X-ray images taken from last one solar cycle, if you talk about. So you can imagine that when sun is magnetically very active, the X-ray emission also is much, much higher as compared to this image which is taken during the solar minima, because there is hardly such magnetic field concentrated region called sunspots. So here very clearly you see these are very, very bright regions. They are corresponding to the locations where you have active regions. I showed you one of the movies earlier where those extreme ultraviolet images were there. So we really do need to understand this. Of course, this is H alpha showing a chromospheric height. I will talk about different layers in the atmosphere of the sun. So this is the advertisement of our Kodaikanal archive. If you go back to the archive and just look at 1st January 1958, you will find there are data in different wavelengths. White light picture gives you the emission coming from the surface of the sun, which we see typically. If you now take other filter wavelengths, here there is example showing as calcium K and H alpha. These are ionized calcium line from certain say 10,000 degree plasma, which represents about say 1200 to 1300 kilometer in the atmosphere of the sun. So atmosphere of the sun has many different layers, and that has a different temperature profile. I will briefly come to that. It's very, very different from our terrestrial atmosphere, because if you go to higher up in the atmosphere, you are expected to go to cooler and cooler places. If you come to Nainital with me, you will find it cooler. But here in the sun, when we go higher up in the atmosphere, the actually temperature is much higher. So this is very unusual, and normal thermodynamics cannot explain that. So it is a non-thermal processes which are responsible for the hot outer atmosphere of the sun, and namely the outermost atmosphere is also called the corona, that you can see only from the space or during the total solar eclipses. I guess some of you had the privilege of seeing some total solar eclipse. That is the time only we can see the outermost layers of the sun, which is beyond say 2000 kilometer height from the surface. So this is, as I mentioned, I'm very proud of this archive because it's now been widely observed or used. And I'm a sort of a proponent of open data policy. I think the community has to push for it, and the next generation also has to push for it. Any science you do, make the data public domain as soon as possible, so that others can verify and others can use the data also for something else, which you don't have that. Every individual cannot exploit all the cream of of the data. So it should be made public as soon as possible. So that's again a big thing which we are looking into in the national level as well. What is shown here, it's a prelude to our ADITYA mission, that if you want to do solar physics even, if you would have just restricted to the ground-based facility, then you would have seen this white light image. Of course, some amount of things can be done. But if you go to space, you can see the extreme ultraviolet. You can see, of course, X-rays. And in the high up in the mountains, you can see some infrared. Of course, you can see infrared from space as well. So this is the electromagnetic spectrum on the top. Modern day astronomy demands multi-wavelength science, multi-wavelength astronomy. And I think for any astrophysical things to probe, because astrophysical objects are in a very highly thermalized atmosphere, they're very multi-thermal in nature. So if you want to see the complete picture, you have to have the capability of space program and ground-based program together. See, one can say that why not just go to space? Of course, you can go to space with a space program, means always there is a limitation in terms of real estate, in terms of power, in terms of the telemetry. So the kind of new experiments what you can do from ground, you cannot do it from the space. So you have to first test things in the ground. So a combination of a ground experiment and space experiment is actually key for any branch of astronomy. And this is an example of that. And you see that when we look at different wavelengths, how much different structures we are able to see. This is something called coronal hole. It appears like there is a hole inside because the temperature is much cooler than the surroundings and so on. And now we know that there is something called solar wind. It's the outermost expansion of the atmosphere of the sun, which comes out continuously from the sun. It gets accelerated from these kind of regions. So it is important that we have all these different kind of data to understand our near Earth environment as well. So this is a picture of a photosphere, which is the visible surface, I said. This is lower chromosphere with a calcium kind of picture. So this sunspot pair, you see, it will be all the way anchored, because as I showed you this animation of these magnetic tubes, they will be actually they are of course emerged from the beneath the surface, and then they go all the way deep into the atmosphere as well. Here you see this small little network pattern. They are the granulations. That's again a direct manifestation that sun is convective inside. When there is a convection, you find these bubbles everywhere. If I go higher up, I will see a slightly bigger structure. These are called supergranulations. You want to study, chaos. You want to study convection theories. This is again another laboratory, because this kind of scales of course, you can do in your supercomputer here, but I'm sure you will be still limited to certain dimensions of your computing boxes if you want to really study, fully, convective simulations. So here it is not only convection, it is magnetoconvection, because your magnetic field is also there inside. So before it comes to computer simulations, sun provides you a lot of insight onto these things. So even you will find magnetoconvection simulation images and in Nature paper and solar observation side by side, that this is a proof of concept that what we do in the computer box really does exist in nature. Of course, you can't show it in our environment, so sun provides you a laboratory for that. So there are many such examples of physics application. Here I go a little bit higher, say around 1600 kilometers with the H alpha. I see those sunspots, but still I see additional filamentary kind of structures. So that means the atmosphere is very much filamented again by the presence of the magnetic field. It's the magnetic field which dictates how the plasma will be structured. So the topology of the field and the environment of the plasma conditions and all that will dictate how these structures will be. So here again, a lot of plasma physics experiment. And if I go high up in the corona, in the X-rays, I still see these sunspots, but I see very, very long tubes. So these are very bright tubes emitting in X-rays. So you can imagine how much energy is confined in this. And if they explode, then how much energy will be injected into the interplanetary medium as well. So this is the temperature profile in the 1D thing from the sun. So essentially this from the surface, if you go higher up to say 500 kilometers, the behavior is normal, the temperature goes down, but then temperature starts shooting up. And this is what is a problem called coronal heating. How to explain that the corona is so hot as compared to the surface, because there is no apparent energy source to maintain this high temperature. And a lot of these magnetic phenomena is now involved in this, explaining this. So active regions on the sun, as I again highlighting that you have these regions where strong magnetic fields are there in the photospheric region. But then I show you multi-layer pictures from EUV wavelengths. This is taken from 171 angstrom EUV filter from a solar dynamic observatory. and this is 304 angstrom. This represents chromosphere. This represents low corona. So as you see, these structures in the high corona is getting much more extended, and these tubes are even much more lengthier, and they show a lot more dynamics as well. So all these dynamics are, these tubes are anchored to the foot points. We call them foot points. So if my foot point gets jostled, I move these foot points, then I am actually building stresses on these tubes, and then the stress will lead to instabilities and all that. So if you want to study a lot of magnetic instabilities, this is again a perfect laboratory for the same. I mentioned about active region. Now let us look at a very quiet region, so-called quiet region. I'm zooming in to this so-called quiet region, and I focus this area. This is a ground-based telescope at US called Goody Solar Telescope, photospheric thing which shows the granulations, and then you see there's lots of these motions because the granules are getting formed. But now I go up in the chromosphere with some, again, H alpha observations, and I see that there are small little spiky jets. They are coming out from these certain boundaries of supergranule. Now I go back and look at where the magnetic fields are. So I see one polarity blue and another polarity red, and I discovered that whenever these blue guys are coming closer to the red guys, there is a magnetic process called magnetic reconnection, and the jets are formed into exactly those locations, and those jets are carrying the energy all the way to high up in the corona. So here you will see that these jets from a space observations, if I look, I will see that whenever there is a jet, subsequent time, travel time we added, you will find brightening in those particular locations. So this is a direct proof of that, this kind of, jet-like reconnection events is producing this kind of jet. So that's again a cut of that. So here you see the surface where these magnetic fields are, killing each other. That produces these jets, and those jets carry the energy all the way up in the corona, and you see this hitting. So again, it's a classic example of multi-wavelength observation. Of course, you can see a huge number of people involved in this. Of course, this is my former student. I got involved. Of course, he moved to China for his first postdoc. But China has 10% time in this American telescope. They bought 10% observing time. So he was the PI of that. And of course, there are Europeans, there are Americans. So this kind of collaborative things are also almost mandatory these days to get access to that quality data. And also, of course, all these ideas to group together and so on and so forth. And if you want to get into a top quality journal in astronomy, this is need of the hour. This is again the example of the magnetic storms. They get tangled up and break apart, and the violent storms come. We call it solar flares. And you see here the flare is happening, and this huge amount of ejecta. And then we will find at the end of this, there are white specks. These are basically highly energetic particles which is hitting the camera, which is situated in the space. In our laboratory, whatever is space, they are being hit by these energetic particles. So I'm sure you don't want to be there to be hit by these energetic particles when such a solar storm happens. Of course, lots of satellites are getting destroyed because of these solar storms every other day. The flares are quick, intense, but when there are bigger explosions, so this is again examples of flares, and these are again multi-wavelength observations of these kind of flares. I see it in 304 angstrom, which represents a chromosphere, low atmosphere, and I see this kind of huge flare happening. And then if I move to other filters and all that, I will see other manifestations as well. So I will probably CMEs are large solar storms that can blast out cloud billions of tons of particles at over 2 million kilometers per hour. You see, numbers are now becoming astronomical in sense. And you see this kind of, and if I see, size of Earth will be something like this. So if this kind of huge explosion happens, it typically takes 1 to 3 days to reach our Earth. But of course, everything is not reaching us because it's a 3D space. It's only the one which is in the Sun-Earth line will reach us. But we need to know where it is coming from and what time it can reach and so on and so forth. So the sun is also the source of radiation and storms. This is the field which called space weather. This is taken again from stereo spacecraft. And as you can see, if I run a movie for just when the sun is very active, just for a few weeks, I see lots of these kind of, ejecta coming up. And I'm sure you don't want to be here into this, blast of, it's just not particles. It has a magnetic field. So it's quite a, adverse condition here. So here again, I'm showing how today combining data from multiple instruments and multiple satellites, we are tracking these ejecta. So this ejecta has come out from the sun, and these two instruments are called coronagraph. These instruments are called heliospheric imager. So we don't look at the sun, we look at the heliosphere, that is the sun earth connecting line, and we are tracking these guys. Of course, this is again projected in the plane of the sky, so we still do not have the correct velocities and so on and so forth. So now we are trying to do stereoscopy, two identical satellites looking at the same ejecta coming out of this. We are trying to go out of ecliptic plane, so combining data from n number of different satellites or different vantage point will only allow us to track these objects to predict when this guy is going to come and hit our near Earth environment. So this space weather business is actually is a very, very important element. And so what is the space weather? Of course, this amount of energy releases light, particles, magnetic field. There are different kinds of variability, as I indicated. Sun rotates typically, it takes about 27 days. So as you can imagine, that this rotation will also have an effect of all these ejecta which is coming out of our place. There is a typical 100 days active region development time scale, like this sunspot. In an active region, you can have 30 to 40 sunspot pairs as well. So that means all these, their lifetime and their association and all that also makes a lot of things in the element. So this is what is Earth's magnetosphere. Thankfully, we have that, and that protects us. But incidentally, the SpaceX, I think you all heard that there were 40 satellites which was lost because there were not a really huge solar storm which directly impacted it, but it changes our interplanetary environment also. It is not always that the storm directly need to impact you, but the trajectory of the satellite or the drag when the satellite is traveling into the interplanetary space is also important. So the drag force was actually different, and they could not control the satellites. So 40 satellites were lost in one go. So I don't think modern day, so this is affordable. Of course, that's why we solar physicists are getting a bit of interest. In fact, there are few companies which has already started in India. I get every other day some email, when is your PhD student finishing, they can get a job. So there is a direct job in industry now. So the space weather prediction is an industry, because all the space companies want to protect their satellite, of course, just not for launch alone, but for their regular operation, because the environment is not very friendly. So this is what happens when solar stuff comes. Normally it would have been very symmetric, but it is not. So essentially because of the solar wind, which is a continuous expansion, and on the top of that, when there is huge ejecta, then the ejecta particles go through this, and that's what gives rise to auroras, right? So you have beautiful auroras, and these are pictures normally available in the northern or southern polar region, because that's a entry point of the particles, and reaction with the chemistry gives rise to beautiful colors. And these are direct impacts. It impacts our radio communication. It impacts our electric power system. It induces a lot of currents, disrupts our radio navigation. Our WhatsApp messages gets delayed for delivery. Of course, it impacts the satellite directly. That will stop the telecast of the cricket match as well. So it is actually a real thing now. It's not anymore just theoretical study application. It has a day-to-day application of our existence. So this entire space, the ionosphere, of course, there are people here also working that it's completely getting populated. There are lots of assets. Richer people are planning to make excursions to interplanetary space, have colonies in other planets. They won't survive unless we predict when it is safe to go out of their shield. There are polar orbits. It's a flights. You take a direct flight from Delhi to New York. It doesn't go through Europe anymore. It goes to polar region to shortcut. And that's actually dangerous. If there is a solar storm, you are getting impact, whatever these beautiful auroras you see, you are also getting exposed to those. Because all these energetic particles. So in fact, it is a mandatory now. If you have a pregnant woman and all that, those flights are banned. You are not supposed to take those flights anymore. So there are, day-to-day, applications of space weather, and that needs to be predicted. With all that, our mission, Aditya, it is a mission where we can always say it's Atmanirbhar Bharat, because all the payloads are built indigenously in different laboratories within the country, different ISRO centers, and there are major payload, centers, like Indian Institute of Astrophysics is building one of the major coronagraph, then IUCA and PRL, which is again now a ISRO center. So, and apart from that, majority of the institutions somewhere or other involved with this mission now for more than a decade. Earlier, it was conceptualized for a low Earth orbit mission, but we got more enthusiastic, and our space agency also got more enthusiastic. They want more adventurous journey, and we are going to a location called Lagrangian 1 point. So Lagrangian 1 point is 1.5 million kilometers away. It takes quite a bit of time to reach there. It's incidentally, it is only ESA and NASA have been able to reach a Lagrangian 1 point. China has not gone to Lagrangian 1 point, so we'll do something ahead of Chinese. So actually, it is quite a challenging mission in terms of its trajectory, and also it's a full-fledged observatory in space. And as you can see here, it's a PSLV launch. So we will make certain, if you have done this exercise of throwing a stone into the long distance, the sling effect will be taken care. And then this is called the near Earth phase. And then this is a cruise phase, and this is insertion phase. In fact, this is very crucial. As you have heard also from the Mangalyaan mission, it was very important that we don't miss to slow down properly and then get into the Mangal's gravity. So here also there is that risk is there. So there are lots of calculation necessary to properly get inserted into Lagrangian 1 point. There are 5 Lagrangian points in a two-body system. Essentially, these are comparatively stable points. Here, you can just think about a location where the force between the satellite and the sun will balance the force between satellite and Earth. So once you reach, Lagrangian 1 point, you can stay there for much longer period of time without, spending a lot of energy. Of course, we still do not stay any space in the space, any point in space. We will do a very large halo orbit around Lagrangian 1 point, but very little fuel will be required because as I indicated, the force balance allows you to be on this. But advantage is we are always looking at the sun 24/7. Anything coming from the sun before it reaches Earth, it has to pass through this. So the idea is that you have a combination of instruments. There are 4 instruments we call remote sensing. We'll look at the sun, and there are 3 in situ instruments which will detect the particles and the magnetic, clouds and other ejecta which is coming, their properties. And solar wind, which is a continuous, expansion of the outer atmosphere of the sun, which is also not very symmetric. Solar wind does, change its properties with solar cycle. It also changes with latitude and so on. So there are lots of variations in the solar wind, which also need to be studied. So you just sit there and study all these properties which are changed. So combination of 4 remote sensing and 3 instruments. I will not get into the full, list of, because there are, really listed here, understanding the coronal heating and solar wind acceleration, initiation of the coronal mass ejection flare, and so on. Basically, we see this ejecta, right? Why this ejecta is happening at certain point of time, not at another time, because an active region is staying for say 1 week to 3 weeks. It is not that we can predict that next half an hour it will eject. So understanding and this initial ejector when it comes, how it will travel. Initial phase, it sometimes, get accelerated, then it slows down and so on. So its kinematic properties and all that need to be studied. So we are going to do that. Then, I will not get into the full list, but if you are interested, I will be very happy to discuss. So as I indicated, we have a coronagraph. Coronagraph is a design which basically an instrument which blocks the solar disk and allows us to see the outer atmosphere, which is called the corona. Incidentally, the coronavirus was named from the coronal images. I don't think many people know about it also. Traditionally, the coronal picture taken during total eclipses showed these, kind of helmets and those streams and so on. And when the biologists saw these virus in the microscope, it resembled a coronal image. So that's why the virus was named, coronavirus, and that's a historical connection. It's not, a story. So we want to see the, corona. Incidentally, we have an infrared channel. We also have a spectroscopy instrument. We have spectropolarimetry instrument. I'm not getting into it again detail. Spectropolarimetry is the next, level of sophistication of measurements of magnetic field, because you have all the 4 Stokes vectors and so on, if you are aware of this. Then we have a near UV full disk imager, first time in space in these wavelengths. The image is mostly what I showed you from the space was, I mentioned some numbers, 171, and so on. They were all in angstrom. So these are 2000 to 4000 angstrom. So this region is called near UV, and there is no space instrument there. 2000 to 4000 angstrom, there are rocket experiments, but no space experiments. So again, from India, when we were trying to do this mission, we were always trying to locate what is missing. This is something, in research always we do. What NASA do not have, what ESA do not have, what is not planned in next 10 years and so on. Thankfully, whatever instruments we have, major instrument what we have, is still not there in space. So there are discovery elements. Of course, hopefully we'll be able to make those discoveries soon. And then there are particle detectors. As I indicated, these are in situ instruments. One is a very cute acronym called PAPA. It's called Plasma Analyzer Package for ADITYA. And then we have 2 X-ray spectrometers. So this is going to look at integrated flux from the sun. It's not going to really have imaging capability in X-rays. As I showed you some X-ray images, which was mostly from the Japanese mission. But here we are going to look at more spectroscopy, like, what are the plasma conditions changes before a flare or during a flare or after flare and so on. So again, trying to find out, new elements. Then we have a magnetometer. So magnetometers are, magnetic measurement probes in the interstellar medium in situ. Like when this ejecta is coming, when we would like to know how much magnetic field is carried by this ejecta and so on. So this is sort of a towered view of the satellite. The big elephant which is sitting in the top is the coronagraph. Big 170 kg fat guy. It's unbelievable. I mean, ISRO, how much pampering they do, Indian scientists. Because if I had proposed this 170 kg in ESA or a NASA platform, the next day it would have gone into a dustbin. Because it's a miniature thing. Space means always, weight is really, really premium. But we sort of cribbed a little bit away. These are for the first time. We don't have this, all the elements and so on. And ISRO has actually allowed us to do that. And that allowed us to build a spectrograph, which is a traditional spectrograph and a spectroperimeter for the first time in space, which others do not have, because it is very hard to miniaturize some of the elements of spectroscopy. And then this is the near UV imager, which I was referring to. So again, we have multi-payload. These are called observatory class mission. It's almost like an observatory in space, because you have 7 different instruments capable of having all multi-wavelength capabilities. So covering different atmospheric layers, remote sensing and in situ observation, establishing the connection between the source and in situ, like where it is coming from. Of course, at the end of the day, it comes from the sun. And then in situ is the effect which you are studying, and the capability to address many scientific problems, which I will be happy to discuss if somebody is interested. Thankfully, ISRO has given ARIES this responsibility of ADITYA L1 Science Support Cell. If some of you are aware of AstroSat mission, which is a very successful mission, our first astronomy mission is AstroSat, still fully functional. IUCA got the support cell. So somehow I could manage to convince ISRO that I'm not involved with instrument building. Give me scope to train people, and this is I'm very happy that ARIES, we have initiated all this activity. We do regular workshops and training and all that. I know one of the students from here did attend one of the workshops which happened just a couple of weeks back in IIT BHU. We were just discussing that maybe IIT Roorkee will also host. We go to different parts of India to train new people, because traditionally what has happened is the guys who build the instrument, they only use the data because they know how to analyze the data. But now these are taxpayers' money, 500 crore project. It is not fair that just few individuals like us will get the fruit of it. So our idea is to increase the user community, and that is only possible if users know a priori about the instruments, what kind of data use. So we have simulated data. We do data analysis workshops. So mornings are lectures, afternoons are always with real data, and then subsequently, if people are interested, one can join more as well. So thank you for your attention. You are most welcome to visit. This is a site at Devasthal. I took the picture just a few months back, and that's our logo of Aditya. Sorry, I took it a little longer. Thank you. Sure. Yeah. Mm-hmm. Yeah. So essentially, actually, there are, since you asked this question, I already backup slide. There are 5 Lagrangian points in a two-body system here. So we are going only to L1. There is another place called L2, which is behind Earth. In fact, JSWT, the James Webb Telescope, is situated there because they don't want to get warmed up by solar radiation. So they are there. Yeah. So your question is, so these are a sort of potential well, and then once you are there, then you need only very little fuel to make stay there for very. Incidentally, the SOHO satellite, one of the ESA mission, was launched in 1995. It is still alive. Still it is functioning. Of course, some of the instruments have got, yeah. So the whatever fuel it carried. So for our mission also, we call it a 5-year nominal mission. Of course, people will ask when it is expected to launch. All the payloads have been delivered to ISRO now. Very, heartbreaking exercises are going on. They call vibration test and so on. They put it in the, shaker and look at, whether they can sustain when it has to travel. So thankfully, majority of the, as far as my knowledge goes, bigger ones have been cleared the vibration test. Because once the vibration test, fails, and it will go back to the lab, we have to fix again certain things and so on. So thankfully, nothing has been shot. So if things go all right, we are expected to launch by June, July. If we miss this, because again, there is a particular trajectory which we have to take, then you have to wait for another 6 months. So that's the current status apparently, we are told. But even today, there was a whole day meeting going on. Even tomorrow it will go. It's called ground segment and the data pipeline and so on. So people are getting ready to fly.
Yeah. Is there a possibility of breaking those magnetic transport?
Yes. So basically what happens is, so the two opposite polarities are connected by these magnetic field lines, right? So they are supposed to be very stable and so on. But suppose, I make a twist and all that. You do that exercise with your rubber band. I think you go on twisting the rubber band and all that. Beyond certain number of turns, the rubber band will snap. So here the magnetic tubes also undergo that kind of stresses. So then when that thing happens, that's what gives rise to solar storm. And you please also note, there is some of the animations and what I showed was an idealized situation, like, one single tube like this, but it is not. In reality, some of the images we will see that there are, hundreds of thousands of, different magnetic connectivity. So that means there is always a possibility of interaction about these two tubes coming to each other, and then the tubes break. So, yeah. Yeah, I mean, monopole doesn't exist, as you know. Having said that, you will always find the opposite polarity somewhere. It may not be in the neighborhood. So reorientation happens. In fact, what happens, since you asked this question, when such big flare happens, the big tubes go up, and then you find after a few hours, new set of connectivity has come. So these are called post-eruptive arcade. In fact, they're also called arcade because you find n number of magnetic fields. They're like, making a new, completely new connectivity. In fact, just to add, this process is under a magnetic topology. If you know topological mathematics model and so on and so forth, lots of things goes into explaining magnetic reconnection before a flare and a post flare, because connectivity will change. And the energy, part of the energy will be released.
Do they exist from the beginning of the world, or they form under the star?
Yeah, again, in a star. Okay, that's again another story. Yeah. So as I said, the magnetic field now we try to explain in terms of a dynamo theory. And dynamo means you need ingredients like this convection. You need a rotation. But again, rotation also is, the sun is rotating differentially. Means, my tummy is rotating slower than the head. You can imagine what kind of stress has been built. And as this guy is coming out from basically this, now we understand that the dynamo is actually being formed in the base of the convection zone. That means convection zone is about 30% inside the sun. And when these tubes are coming up, they are getting into all these stresses. And also there is a Coriolis force. I did not go into that much of details. So because of the Coriolis force, these, two poles are also, bit inclined. Now where this guy will come up and all that depends on what are the parameters of rotation, what are the numbers for convection. In case of different stars, these numbers are different. So all stars, magnetic stars, which are in having a convection zone. So at a different stage of a stellar evolution, the convection zone, how much percentage inside and all that is all dictated. When sun becomes older, the star can become fully convective. So there are different, things happening with the understellar evolution. But since you asked the question, lots of magnetic stars are there. Unfortunately, we do not have so much magnetic field measurements of other stars. This is a completely brand new area where people do work. And again, our understanding of the sun helps our understanding of the magnetic stars as well. Yeah. Very good, very good. So I was building this story a little bit. So what is happening is, now we understand these sunspots are like a big tube. So the big tube at the base of the convection zone, when they're coming, they're also dragged by the rotation. So the equator is rotating faster than the pole, as I mentioned. So that will have a, particular, when it comes, there is a drag also. So this is called a Coriolis force in a rotating frame of reference. So depending on the numbers and all that, it will, at the beginning of the solar cycle, the sunspot appear at certain latitude. It only appears in 30 degree to 40 degree latitude. And then with the progression of the solar cycle, when the sunspot cycle is going into the stronger, and then eventually will die and all that, these sunspots will not appear high latitude. They will appear in lower latitudes and so on and so forth. So this is completely driven by this dynamo process, which is a cyclic process. And there all these ingredient goes into convection zone, convection, rotation. There is another element. Since you asked the question, let me add this. There is something called a meridional circulation. What happens is, inside the convection zone, we have looks like a belt. And that belt, the speed of the belt actually also crucial for making out where the sunspots are coming one particular latitude and all that. Suppose this belt is slowed down, then our cycle length also will go up. In fact, there is a theory which says that this is called meridional circulation was very weak during the Maunder minimum. I mentioned that 1650 to 1700 there were no sunspots. So that's one explanation. Probably that belt, it's like, you know, you go to the airport, your bag is supposed to be delivered. Your belt doesn't come, your bag is not delivered. So the break, depending on the speed of the belt, you know, the parcel has to be delivered at the right latitude. Yeah. So you are in a way right. So depending on the what phase of the its evolution it is, as I indicated, sun is in its middle, you know, lifetime. I mean, I'm just crossing my middle age. So you see the manifestations and all that. Huh? So because of it is main sequence, there is a particular stellar evolution. It spends maximum number of years in the middle age in a stellar evolution. So right now we don't have to worry about for next million years and all that. But we do now discover that that internal circulation and all that probably, you know, changes because of something else happening inside the sun, which we still do not understand why it is so and all. Having said that, I will say that when in a nature, whenever there is a non-linear process, means, you know, we cannot really explain by simple, you know, thermodynamic, I mean, equations and so on. Such, you know, perturbations sometimes blow up, sometimes it dies down, and so on and so forth. So nature is very chaotic. We call it turbulence, and sun is inside is very much turbulent. So it's hard to really predict what is going to happen. So in fact, if you want to study turbulence, sun is again a very good laboratory for that. I mentioned about chaos. It's just you know, another way of, and not only inside the sun it is turbulent, even the atmosphere of the sun is very turbulent as well. Good point. So what we understand is this, normally the magnetic field confines plasma. It tries to get a sort of quasi-static equilibrium structure and all that. So magnetic reconnection is a forced situation, like some other motions or twists or instabilities is driving that. And because of this process, energy is released. There could be other instabilities also. I mean, it's a very good point which you realize. That can also give rise to CMEs. For example, there is an object called prominences. These prominences are huge magnetic clouds, you know, in the atmosphere of the sun. They live for months to, you know, several months and so on. They are stable structures, multiple forces, they balance it and so on. But somehow if that, you know, some instabilities generate, then this huge cloud of plasma which is floating, it will erupt, and that will give rise to CME as well. So it is, but again, some people say, why this guy is, you know, erupting? Maybe there is a flare which triggers this eruption. So there is could be a flare connectivity somewhere. But the main ejecta which comes from the prominence is because of the instability. So often this, since you mentioned CME flare connectivity is also a very important study, because we all need to do that for predictions. So CMEs, if you want to predict, then you have to understand what are the sources of these CMEs. And as you rightly pointed out, it's just not always the flares. It could be, you know, these prominences. So we do follow the prominences as well. So we have this suit instrument near you. We will be preparing a catalog from our center as well, so that we have a complete knowledge about what are their different sizes, what are their morphology, why you know, some are you know, ejecting, why some are leaving for 7 days, some is living for, you know, several months. So all these things can be studied statistically, so to say. Lot of computer application actually. The other thing is we need a lot of good computer engineers and AI experts to handle such a, you know, huge volume of data, because it's going to generate, you know, too much of data. More questions? Sure. I am here.
We have 2 points. you disconnect. When this is broken, then points are separated. So it will take certain time, it will be very small, but when single point to the some other point. But it's like a magnetic monopole very, very small.
Yes, yeah, it is possible that, but again, as I said, for a few, yeah. So for few moments, still a new connectivity has not happened. So it is isolated. I would say rather than the monopole, it is isolated. Like it is always in pair, but one pair has got disconnected or disappeared. So any reconnection is a cancellation. So it's called flux cancellation. If one guy is bigger than the other, of course, when it's interacting, the smaller guy is eaten up by the bigger guy, and you are remain with some amount of that big fellow, and that is isolated for maybe a few minutes or few hours maximum, and then it will get connected with the neighboring flux. Yeah. So this dynamics of this magnetic things are very important. I show you a enlarged thing of the quiet sun, so-called. You saw so much of magnetic field. This Salton paper there is there everywhere actually. Sunspots are only the big ones, which are say 5,000 kilometer size, and the small guys are only 100 kilometer size. And those small flux tubes, we call it, to model it theoretically. These are big flux tubes, and these are small flux tubes. They have not been observed in the past. Of course, we didn't have a high resolution telescopes for that. So it's only, even my PhD period, this is the first paper came out of the small flux tube observation. And now we are really studying their dynamics and effects and so on. Yeah, so it's about 50 kg. I don't remember it's a good point. It's a few millimeter only. Yeah. So that is the big challenge. That's a big challenge. The rotation has to be maintained with a very, very high accuracy. Yeah. So again, this part is built in Belgium. We have not been able to build. The motor is Indian, but the specs, everything was given. Even the bowl, the material, and all that has come from abroad. No. The bowl is just rotating. So the Mercury has to sit on the top. So gravity is there. Yeah. So there is a very small friction. There is oil, which sort of allows to slightly float. I would say that way, to avoid the friction and all that. Yeah. Just so that the motor and the thing, there is a little bit of oil surface, which I know as a touching point, so that the friction doesn't, even the movement of the neighboring. You see, typically what happens is any telescope, they're always isolated from the neighbor's thing. So we need a pier, and the pier structure is actually disconnect from the rest of the building altogether, so that the telescopes just sit with the pier. It doesn't share any vibration, because we are talking about 1 arcsecond in the sky with accuracy. Any small little movement will destroy this. So here I see that point is because we cannot have of course there is a pier underneath that building also, that is there. So this particular guy which is sitting underneath, there is a pier, and the next to the building is isolated. But then when the bowl is also sitting on that, there is because it is always rotating and all that, I guess to avoid the friction, they have a little oil. Yeah. Yeah. So since you asked the question, in fact, this particular liquid mirror telescope was there in Canada, and they were not using it for astronomy purpose, but for defense purpose. So NASA had built such 6-meter class telescope. They had difficulty because of the snowfall. Because in the mountains in the Canada and all that, they could not run it. We have problems here during rainy season because of humidity. But you come to Devasal, actually winter is best for the night sky observation, because the sky is much clear in winter. Of course, when it snows and all that, we have to shut down. I mean, But again, the mirror will not stop. It only we will stop the top thing. There is a slit. We just close it, because to build the mirror again, it's a long process. The balance and all that. So there is 2 sets of backup power, UPS and all that. Once the mirror is formed, several months it will run continuously unless there is a problem. So even if the night, after the night, I mean in the morning we don't observe, of course, but the mirror is on all the time. So that consumes some. Yeah. This has not been fully verified, because as I said, we had only 7 nights of observation. So still image, sort of restorations and all that is happening. And since you asked the question, how deep is the sky you can go, depending on a lot of things. Of course, the sky transparency has to be good, seeing has to be good. What they're trying to do is, as I understand, again, I'm not an expert in this, they're going to stack a lot of images, even several years, to go deeper, because you know precisely where this object is expected to be in the sky from that longitude and so on. So by adding several images and all that, they expect it to go to much deeper in the sky. So these numbers are still not evaluated, I would say. A lot will depend on at least a 1 year of data. Yeah. No, you cannot. So that's a disadvantage. That's a disadvantage, because Mercury gir jayega. So that's a disadvantage of this kind of telescope. It is always looking at the zenith. It cannot be. Yeah. So I mean, that's the conventional telescope big advantage you can. But the idea is very different here. You are looking at large field of view. It's yeah. So essentially discovering transients, because once you know a transient is there, then you point your bigger telescope with a smaller field of view to that object. So that's the idea. Yeah. So these things are called Cassegrain, but in the prime focus itself there is a camera. So just to answer you, of course, in the prime focus you can have another mirror and divert it to a spectrograph and all that. That is possible. It is not possible. But as a first phase, I don't think they are looking at it, because the deep sky imaging is something which once you achieve that, then a spectrograph is possible. So basically, you can divert, place some mirror and divert that parallel beam to somewhere else. Yeah. Mm-hmm. Straight. No, it appears, you do this exercise. So you have to build a momentum. Apparently, this is, of course, you have to take gravity assist as well. So other objects, gravity. In fact, if you want to go even further distance, you have to take gravity assist of other planets. You get first into other planets' gravity, and then again, spin up, and then go out of that. You basically make a stepwise journey, so to say. So it appears that this is what is is much better fuel efficient wise. You see, of course, you can try to get straight as well, but then you will exhaust all your fuel. Yeah, it's a 3D dynamics. It's already only placed in one plane. That also you have to keep it in mind. Of course, we do it in ecliptic. It's not that we are going out of ecliptics. That is also there. Now, solar orbiter, there is a mission which is flying out of ecliptic. So then, for the first time, we will look at the polar region of the sun. You see here, the polar region of the sun is always, we really do not know what is happening in the polar region, because we are looking at it in the plane of the sky. So if you are to really see the poles, you have to go up, right? Not in the ecliptic plane, but you have to go up and then see from the top. And solar orbiter, which is a ESA mission, they're trying to do that. and their trajectory, if I show you, पागल हो जाएंगे आप 4-5 साल लग रहा है उसको थोड़ा ऊपर जाने के लिए. Okay, so you know, mercury is a liquid. So you are using a liquid to build this mirror. Normally, mirror is built of you know, glass material. There are other silicon carbide and all new composites are also coming, but traditionally, mostly it is glass, which is there as a primary reflecting surface of a telescope. So this is quite, you know, unique that you are using mercury for the, you know, telescope. So that's why it's called liquid mirror telescope. The mirror is built of liquid. What liquid? It's mercury. Oh, she has another question. You have to you know, entertain it. Yes. How can we see things which can't be seen from the telescope? Okay. So what happens is, in a traditional telescope, what we do, we get this light of rays from the distant object. It gets into parallel rays, and then you have either a lens or a mirror to reflect it and get into a focus. I don't know whether you have still studied in the school a lens. So there is a focus, and in the focus, if you keep an eyepiece and you look at your eyes, you can see it. But these days, modern day, you know, we don't have that. Essentially, we feed all these, you know, convergent beam into our detector. So detector means, you know, your camera. You have your mobile camera. So that also is actually collecting these light rays and focusing it and imaging it. So we use a detector. It can be your mobile detector. We have a little more expensive detectors. In fact, since you asked the question, you know, in astronomy, we had the first CCD detectors in 1990. The first CCD detector came in 1990. In fact, astronomy often have actually forced the technology to develop, because astronomers look at few photons. So the very low photon count devices, earlier it used to be photomultiplier tubes and all that. So this detector technology, what everybody is using today, was demanded by astronomers, that we have to have devices which will multiply these photons and have, you know, some way of looking at it better. So radio astronomy, the, you know, Wi-Fi, all have come out of astronomy, you know, demands, and actually experiments as well. So so we need these cameras, and the cameras have become very good for us these days, and we are sending these cameras to space as well.
So why is the sun rotates faster? Velocity is faster.
What do you mean by velocity? I mean, it's an object which is rotating about its own axis. Huh? First of all, you have to think about the object is a plasma blob. You have taken jelly, any jelly object and all that. You take a lump of jelly and start rotating. There is no reason actually it will rotate as a solid body. If sun would have been a solid body, then you would have seen, you know, all parts rotate faster. Why it rotates that amount, we still do not understand, of course, but there is no reason for a plasma blob, because it's not a solid, it's a blob, to get D-shaped, you can say that way. So you know, the equator is rotating faster, so it's like bulging out, you can think it that way as well. Come down. Okay. Thank you. Thank you very much.
Thank you very much for wonderful, spectacular lecture.
Thank you.
Very
Thank you very
interesting.
much.
You can see from the question.
Thank you very much. Thank you. Thank you.